Hello, hello, hello. This is Nicholas, and I'm not going to be doing a video on variation of parameters again. I'm doing a video on the second order Cauchy, I always say it wrong. It's not Cauchy, it's Cauchy-Euler differential equation. And so this equation has the form ax squared y double prime plus bxy prime plus cy prime equals 0. This is one of the few second order differential equations with variable coefficients that can be solved analytically without a power series expansion. Most of the variable coefficients require a power series expansion. So if we look at this, you look at this and you say, well, what might y be? And hopefully you have the idea. Oh, I don't know why I wrote a extra prime there. Hopefully you have the idea that y should be x to some power. Why? Because when you differentiate it twice, you lose two of those factors, but then you gain two when you multiply by the x squared, or when you differentiate it once, you lose one of the factors, you have r minus 1, but then you gain another one by multiplying by this x, and then you're just multiplying by the original function. So it should make sense to you that the general solution to this Cauchy-Euler equation is going to be in this form for the second order form of this equation. So if we plug that guess into the differential equation, we get ax squared r minus 1 times x to the r minus 2 plus bxr times x to the r minus 1 plus cx to the r equals 0. And this x squared, x to the r minus 2, x to the r minus 1, and x. So we can pull out a factor of x to the r. That's ax squared or not ax squared, I'm sorry. AR squared minus AR plus BR plus C equals 0. And I'm gonna divide by this because well, for one, if I have x equals 0, I mean the identity solution 0 is not all that interesting, so I don't really care about that one. And so we obtain the auxiliary equation for the Cauchy-Euler equation, AR squared plus B minus A R plus C equals 0. And so there's three different cases, just like with the second order homogeneous differential equations with constant coefficients. We can have two real distinct roots, or one repeated root, or two complex roots. If we have the two real roots, just like how we did with the second order homogeneous constant coefficient differential equations, the general solution for that case will just be c sub 1 x to the r sub 1 plus c sub 2 x to the r sub 2, where r sub 1 and r sub 2 are the roots of this auxiliary equation. Case 2 is when we have one repeated root. So in other words, this factors into a perfect square. Now it turns out that I'm going to make another video using reduction of orders to prove this. It's similar to the second order homogeneous equations, but it's a little different. The first solution or building block is c sub 1 x to the r, and I don't really have to say r sub 1 or r sub 2 because there's only one repeated root. And then the second one is c sub 2 x to the r times the natural log of x. and we multiply it by this natural log of x to make sure that our two building blocks of our fundamental solution are linearly independent. And I will show in another video why it's specifically the natural log and why not some other function. Then we have case 3, where we have two complex roots. So if we have two complex roots, then we would have x to the a plus bi and x to the a minus bi. So let's consider that first, x to the a plus bi. That's, well, x to the a times x to the bi, which is x to the a times, now I can write x as e to the natural log of x. So that's e to the b ln x I. So that's x to the a times cosine of b ln x plus I times the sine of b ln x. And that's the form that you will build your solution based off of. So you can multiply that together, and of course it's a linear combination. So our general solution is c sub 1 x to the a cosine of b natural log x plus c sub 2 x to the a times the sine of b natural log of x. And those are all three possible cases that could happen. As an example, I think the complex roots case might be the most tricky, so I'll do an example of that. If we have x squared y double prime minus xy prime plus 2y equals 0, our auxiliary equation is r squared, because a is 1, plus now we do b minus a. So b is negative 1, a is 1, so that's plus negative 1 minus 1, or in other words, r minus 2, r squared minus 2r plus 2 equals 0. And I'm going to make this r squared minus 2r plus 1 equals negative 1, r minus 1 squared equals negative 1, r minus 1 is plus or minus I, and r is 1 plus or minus I. So our y, our general solution, is c sub 1 x, just x to the 1 there, cosine of b, which is also 1, so cosine of natural log of x, plus c sub 2 x sine of the natural log of x. And that